Welcome to Lecture 4 of Advanced Inference and Graphical Models. We have our reading assignment and also the outline of what we've been doing so far. We've been discussing trees, and what we're going to be doing today is talk about non-trees and perfect elimination graphs and introduce triangulated graphs and see how triangulated graphs and what is a consequence of doing the elimination process on any graph is very, very related to what we've already been talking about, namely trees. And that might seem surprising at first, but it actually ends up being very natural. But before we do that, let's do a little bit of a review and also see if anybody has any questions. Where we went from elimination, the process of eliminating variables, which we saw as a graph theoretic operation of either basically taking a vertex's neighbors and connecting all of them pairwise, and then removing that vertex and all of its incident edges. That's equivalent to the process of summing out a random variable in a product of factors. And we saw how when we sum out a product of a variable in a product of factors, it creates a new factor which has coupled together all of the factors that have been involved in that summation. And similarly, in the graph, we saw how eliminating a variable couples together all of the neighbors of that variable, so that that new bundle of variables, that new clique, essentially allows for a factor that involves all of the variables that are introduced in that new clique. And that clique is called an elimination clique. We will see that today. And we also saw how that process is identical to this form of message passing, where essentially what we do is we gather together the messages coming from everywhere but node I, and then we multiply them in along with the channel between I and j, and then we sum out j, and that becomes the message from I to j. Okay? So that was what we saw last time. We also saw how if it's the case that we're interested in computing more than one edge marginal at a time, that many of the messages were redundant. Namely, for example, in this case, we have all these messages here are redundant with all of these messages here. And if we were smart about it, we wouldn't send them multiple times. We'd send them only once. And that's indicated by this graph here on the right, where you can see that we have blue and red edges along the same, blue and red arrows along the same edge, which indicates a redundant message. And so the blue arrows are the messages that are necessary to compute the marginal along the blue edge, and the red arrows are the messages that are necessary to compute the marginal along the red edge. And since there's so much overlap, or even if there's a little bit of overlap, we would probably not want to do them redundantly. And we also saw that we can at least conceptually think about routing the graph at every edge and sending all messages towards that edge. And what we're going to be left with is, if we don't indicate the redundant arrows, what we're going to be left with is, for every original graph edge, there's going to be a message sent along both directions on the edge. And so what we can just do is identify a protocol that allows one to start sending messages in a tree, which will end up, if all messages are sent, will end up with each edge being annotated with an arrow in both directions, which then can be used to compute the marginal along any edge. Because, for example, let's say that we're interested in computing the marginal along this edge. We would gather this message, this message, this message, this message, and this message. And that would give us enough information to compute the marginal on that edge. And notice that the messages that we've gathered together are a combination of red and blue edges. And in some sense, there really doesn't need to be any distinction between red and blue anymore, because red and blue came from the fact that we were only looking at 2 edge queries. But here now we're, in some sense, looking at all edge queries. And the more edge queries we do, the greater the efficiency of this process is. If we are interested in all edge queries, which is, for example, what we are typically interested in when we're doing machine learning, when we're trying to learn the parameters of the factors associated with an edge, that's the information that we would need to do. And we identified something called the message passing protocol. Message passing protocol, again, was essentially a set of rules that says basically you're allowed to send a message out from a vertex as long as you've received a message from all of the other vertices. Right? Now, it means if you received a message from everywhere, you can send it out anywhere. But if you received it from n-1 of your, or let's say k-1 of your incident edges, then you can send it out of the kth edge, incident edge. And moreover, leaf nodes in a tree, which we know there to be 2 of at least in any tree, leaf nodes, since there are no other edges, we can always send out from a leaf node out into the graph. And that basically means that sort of corresponds to the starting point. Now that insight is critical, because what we're going to be doing today is generalizing that to arbitrary graphs, not just trees. The same basic idea, there's going to be an analogy of a leaf node in any arbitrary graph, as you're going to see, to some extent. Anyway, so we talked about the collect evidence and distributed evidence protocol, or procedures, which when we run them, we argued obey the message passing protocol. The collect evidence procedure is essentially a post-order tree traversal. The distributed evidence is essentially a pre-order tree traversal, and we do these 2 tree traversals, and that essentially gets us to the stage where all original graph edges have been annotated by both arrow directions. We also talked about querying at an arbitrary S. If it was the case that S constituted a subtree of a tree, then that would be very easy. We would, in some sense, in some loose sense, root the tree at the subtree and send messages towards that subtree. And then we would have a very nice R-squared representation of the set X of S that we're interested in. But in general, when we are interested in a query X of S where S is not a subtree, that induces additional edges in the graph. And that's a consequence of Rose's entanglement theorem, which we stated last time. And I thought should have done this figure last time. But basically, Rose's entanglement theorem can be stated in the following way. So let's say you're looking at V and U. So you're looking at this edge here. Okay? And basically, what it's saying is the following, is that red edge exists in the graph G prime. So G prime, remember, is the reconstituted graph. That red edge exists in G prime if and only if it's the case that in G, the original graph, there exists a path between V and U consisting of vertices that have been eliminated before either V or U. Okay, so if all the stuff that's sort of highlighted in yellow is eliminated before the vertices incident to the red edge, then that red edge will necessarily exist. Now that also corresponds to the very simple case when V and U are already connected in G, the original graph, because basically there's a path and there are no vertices other than that edge on that path. And so that also allows for G prime to have, and basically says that the G prime has the edges that are in G already. And so basically it means that G prime will only have a superset of the edges. So Rose's entanglement theorem is a problem that we want to try to surmount. We also defined something called a perfect elimination order, which we said that sigma, which is an ordering of the vertices, sigma is sigma 1, sigma 2, sigma 3. It's an ordering. It's perfect if it's the case that when we use that ordering to eliminate the vertices, that there are no additional fill-in edges added. And so when we look at the reconstituted graph, it's the same as the original graph. And so for a tree, there's always a perfect elimination order, because we always have leaf nodes. And whenever we eliminate a leaf node, a leaf node basically by definition has only one neighbor, and so we're not adding any fill-in edges. But we also saw that for arbitrary graphs, there isn't necessarily a perfect elimination order. And here's a graph, which I think I finally figured out how to plot so that it doesn't look like a cube. This is meant to be a planar graph. And so using this ellipse shape, it doesn't look two-dimensional anymore. And you can see that there are good and bad vertices first to eliminate. For example, x4 would be a bad one because it would couple together all the remaining vertices if we were to eliminate that. This would be a better vertex to eliminate first. But on the other hand, if we were to eliminate any of these other vertices, like, for example, that one, it would necessarily produce fill-in. And so on and so forth. So there are graphs, unfortunately, that do not have perfect elimination orders. And then, so this is actually just a lemma, which we stated, I think, a number of times, and we're stating it here formally now. And what it says is the following. It says, from a computational perspective, not from a, in some sense, statistical perspective or from a number of parameters perspective, but from a computational perspective, it's saying that the reconstituted graph that we get after we run elimination is essentially the family that we're working with to begin with. So if computation is your prime objective, then you might as well start with the graph that was reconstituted, if you're insisting upon using that elimination order. Now, maybe you have a different elimination order, but if it's a graph that doesn't have a perfect elimination order, no matter what elimination order you use, it's going to produce some fill-in. And so no matter what elimination order you're going to use, you're going to be essentially computationally working with the family, that elevated family that corresponds to that reconstituted graph. Okay? Now, if it's the case that the elimination order happens to produce no fill-in, which of course means that it is a graph that has a perfect elimination order, it means that you're sort of okay, that you're doing a good job, at least that you're not elevating the family computationally. The other thing that's important, and this is a new result, is that if we use sigma, if we use the same order a second time, like what if we start from the reconstituted graph, and then we start eliminating the vertices again in the order that we eliminated them in the original graph? That will be a perfect elimination order. And that's important enough to be a lemma. So basically, the lemma states that when elimination is run for a second time on the reconstituted graph, using the same order that we used to produce the reconstituted graph, then the set of neighbors of V at the time V is eliminated is the same whether or not V was eliminated in the original graph or whether V was eliminated in the reconstituted graph. Okay, so that basically means that when you eliminate a vertex, you look at the original graph. Okay, you start eliminating vertices and you get to some vertex, and you eliminate that vertex and you look at its neighbors. Okay, and then you look at the reconstituted graph and you run the same order. You use the same order. You eliminate all of the vertices and you get to that one vertex that you're talking about. The set of neighbors of that vertex in the reconstituted graph and in the original graph are identical. So that is something that needs proof. But basically, here's how we prove it. So any neighbor of V, so V is any arbitrary node. Okay, any neighbor of V in the reconstituted graph must be due to either it being an original graph edge, namely it wasn't due to some fill-in, or it must be due to some fill-in edge between V and some other node that was not an original graph neighbor, right? So like you're at this point V, and you're looking at its neighbors, and there's only two ways that it could have a neighbor. Either it was an original graph edge or it was a fill-in edge, right? So that seems pretty straightforward. So all of the fill-in edges, so all of the neighbors of V that are fill-in edges, all of them must be due to elimination of nodes before V. And the reason why is because after we have eliminated V from the graph, there can't be any additional edges added to V, right? Because V is gone. After we've done eliminated V, any additional elimination guys can't add any neighbors to V. Then thirdly, at the point at which V is eliminated in the original graph and the point at which V is eliminated in the reconstituted graph, it's basically the same. So basically the same previous set of vertices have been eliminated because we're using the same elimination order. So we start eliminating these vertices, we get to this point here. So the history of elimination is the same in the original graph and in the new graph, in the reconstituted graph. So we have the same set of previous nodes that have been eliminated. So what that basically means is that any neighbors of V in the reconstituted graph have already been added in the original graph at the point that we eliminate that vertex V. So that's basically saying any neighbors of V in the reconstituted graph have already been added to the original graph when V is eliminated in the original graph. So basically it means that at the point that you eliminate V in the original graph, it has the same set of neighbors as in the reconstituted graph. Hence, the theorem is proved. So that basically means that's really important because it means that A, you found that when you redo that elimination in the reconstituted graph, every vertex has the same set of neighbors as what you encounter in the original graph. But B, it's going to allow us to start talking about the computational consequences of that particular elimination order in the final graph, in the elevated family, just by looking at the elimination process in the original graph. And we're going to see this here. In fact, here's the question.
So if we are trying to infer a distribution for, say, a couple of nodes in any graph, so will the distribution which we would have got from the original graph and the one which we get from the reconstituted graph be the same?
So remember, we're only really talking about families here. We're not talking about a distribution. The idea of a graphical model is to be working with families of probability distributions. And then when we're doing the elimination process on a graph, we are adding edges to the graph, which is elevating the family. So I think I can interpret your question in the following way, by saying, is it the case that any member of the original family gets rejected in the elevated family? And the question is no, because the family is always growing. So if you're developing a computational strategy for solving inference in any member of the larger family, it must necessarily be the case that if it's valid for any member of the larger family, it's also valid for any member of the original family, because the original family is a subset of the distributions. You're valid for a bigger set, you're valid for any subset of that set. So therefore, the distribution is the same. If you're working with a particular distribution, of course the distribution is the same, but what's really important is that you're not violating any of the properties. You're not basically making invalid any of the properties of the original distribution that you're working with. You're not, like, for example, cutting out chunks of the family. That's essentially more along the lines of approximate inference or structural learning, which is something that we will be talking quite a bit about in this quarter, but not right now. Right now we're still talking about exact inference. Yep.
Why do we not put like an n in that big O? Like if we're in a tree, then it's...
Oh, in this lemma?
Yeah.
Yeah, so in this particular context, I'm basically assuming n is a constant. This is for fixed n. Obviously, if n is not a constant, you have to put an n in here as well. You're talking about like right in here?
Yeah.
Yeah. So right now we're really just talking about just the complexity as a function of the largest clique size. Let me state this theorem before you ask a question about it, because I haven't stated this theorem yet. But are there any questions about, I guess, this other theorem? So since you already understand this, let's move on to the next one. So, no. So, okay, so here's the next lemma. So basically what it's saying is that given an elimination order, so we've got some ordering of the variables, okay? The computational complexity of the elimination process is order r to the k plus 1. So remember, all random variables take on r values for simplicity. And you're right, we're not talking about n right now. We're just talking about sort of the worst case complexity. So n is a constant from the perspective of this discussion. And what is k? So k is the largest set of neighbors encountered during elimination. So basically, you're eliminating variables, and each time you eliminate a variable, that variable has a set of neighbors. And k is the largest set of neighbors you encounter as you're going along eliminating variables. And moreover, this k is going to be the largest clique, or I should say k plus 1. This refers to k plus 1 here. So this is k plus 1. K plus 1 is the size of the largest clique in the reconstituted graph. Okay. So how do we show this? So when we eliminate, so remember this notation we had last time where when we're eliminating graphs, so G0 is the original graph, G0. And then G1 is the resulting graph after we've eliminated the first variable. G2 is the graph after we've eliminated the first two variables, and so on and so forth, up until we've got, I guess, Gn minus 1, where we've eliminated all but the 1. And then Gn, of course, is, in some sense, the empty set. So we are eliminating sigma I. So sigma I is the vertex in order I in the graph Gi minus 1. Okay? So when we eliminate sigma I in Gi minus 1, so eliminating that will cost, this should be sigma I. So eliminating that will cost r to the L, where L is equal to the set of neighbors plus 1. That's basically, we get that from the mathematical expression of eliminating. When we sum out of variables, basically it's 1. It's the variable that we're eliminating plus all of the neighbors in the variable. So those are all of the variables that are involved in any of the factors that are coupling together with that vertex that we're eliminating. And so the overall cost will be the max over all of those things, which is just r to the k plus 1. Now the next thing we need to show is that the largest clique in the reconstituted graph is equal to the complexity. So let's look at this reconstituted graph. Okay? And let's assume in the reconstituted graph that the largest clique size is k plus 1. So now when we rerun elimination on that graph, there's going to be no fill-in, right? Because we've now identified, by doing the elimination and adding the fill-in, because of the neighbors in the original graph and the neighbors in the new graph are the same, since the neighbors in the new graph are the same as in the original graph we've added the fill-in so that the neighbors become a clique. In the reconstituted graph, the neighbors are a clique, and so therefore there's no fill-in when we run elimination again in the reconstituted graph. So there's no fill-in. But the cost of the elimination step when we reach the first vertex of that largest clique, so you're some big clique over here, right? And you've got k plus 1 guys, right? And so this is the first vertex. It's going to have k neighbors up there. And the cost of that first vertex is going to be k plus 1. But at that point, there aren't going to be any other neighbors, right? Because of the fact that the theorem that we just proved, namely that the neighbors are the same in the reconstituted and the original graph. So only the neighbors of that largest clique are going to be the neighbors of that first vertex. And then this is then the same cost as whatever that cost was incurred in the initial elimination procedure. Why? Because of the previous lemma that we proved, because it has the same set of neighbors. So let's write another figure here. So if we've got, let's say that this is some clique, let's say that this is some clique here, and here's some vertex v, and it's got, say, k neighbors, right? So we know that all of these neighbors up here are going to be a clique in the reconstituted graph, because the neighbors of v in the original graph and the neighbors of v in the reconstituted graph are the same. But that must mean that the neighbors of v in the original graph was k, and so that's going to cost k plus 1. But that happens to be the largest clique in the reconstituted graph. So that basically proves the theorem. So the largest clique in the reconstituted graph is the complexity of doing elimination. So this means that any perfect elimination ordering on a perfect elimination graph. So what is a perfect elimination graph? A perfect elimination graph is a graph that has a perfect elimination order. And so any perfect elimination order on a perfect elimination graph will have complexity equal to the size of the largest clique. At some point or another, no matter, we're eliminating all of the variables, at some point or another, we're going to hit that largest clique. The first variable of that largest clique is going to have that complexity. Okay. So there are going to be a bunch of theorems and proofs in today's lecture. So feel free to ask questions. This would also, by the way, be a good lecture to go back and review the video if anything is not clear. Or you could just read the theorems, because I think the theorems in the slides are pretty complete. The question?
Yeah. So far we've assumed that kind of the support of each node is constant R, right? Like, so if we change that assumption, is it the perfect elimination relax that assumption.
Right. So if it's the case that the random variables have different numbers of values, so I like to say that the domain size of the random variables are different. So it could be the case that you have a very, very large clique in terms of k plus 1 with only binary variables, and a very, very small clique with, say, n-ary variables where n is 1,000,000, in which case the small clique is going to have more cost than the large clique. But asymptotically speaking, as k grows, even if the variables are binary, at some point you're going to have exponential growth in the clique size, whereas only polynomial growth in the random variable domain size. So from an asymptotic complexity theoretic perspective, we're really interested in the exponent. And the clique sizes are basically the size of the cliques are the value of the exponent. And so we sort of are focusing on that. But in practice, when you go to implement this, and I've actually personally implemented this a number of times, when you go to implement this, there are many real-world practical issues associated with large cliques of binary variables and small cliques of big variables. But on the other hand, I mean, exponential cost does catch up with you fairly quickly, because even if you have all binary variables, if k gets big too fast, you forget it. And so usually what one does when the clique sizes are big is you have to use some form of approximate inference method. There are strategies that people use to try to do exact inference. And of course, fast implementation makes a big difference. You can sometimes get a factor of 5, factor of 10 difference between a fast and a slow implementation, or a fast programming language or a slow programming language. But at some point or another, that exponent's going to catch up to you. Now, the other part of your question is, well, how do you measure the complexity? So the complexity is more, rather than just r to the k plus 1, it would be the product of the domain sizes of the variables in the clique. So if you have a clique where maybe one variable, the first variable has domain size r1, the second variable has domain size r2, and so on and so forth, the cost of that clique would be r1 times r2 times r3 times r to the r sub k plus 1. So you just multiply. It's the same thing, except that you have different r's. You're multiplying, and that's called sometimes the state space of the clique, because you effectively need to enumerate that many values in some sense, because things are all coupled together. But so the final word on that question is, yes, we're doing a bit of simplification, but I think it's sufficiently complicated without adding this additional nuance, which, like I said, is important in practice, but from the perspective of getting the global, big picture idea of what's going on, it need not be exposed to you at this point to get a general understanding. Question?
That means it's preferable to have a feature, for example, color. I will have a color with a domain, let's say red, blue, and other thing, instead of create several binary color indicators, whether it's red or blue, whether it's red or whether it's blue. Because in that case, I will have a 2 to the k, let's say I have a k colors, 2 to the k kind of complexity, versus if I compact all the color into one feature, then that domain is k.
Yeah, I'm not 100% sure I understand the question, but basically it is related to coloring and constraint satisfaction problems, and like things like map coloring and constraint satisfaction. In fact, these things, graphical model inference corresponds to like satisfiability problems in Boolean logic, and also constraint satisfaction problems, which includes things like map coloring. But I'll try to, I think I answer your question by saying that that when the domain sizes of the random variables are different, one does have to pay attention in practice. So like I said, for the same reason as the lots of binary versus few n-ary. So I hope if that doesn't answer your question, maybe you can come up during the break and ask me. Okay, so let's just do a little bit of a recap, because there's a couple of different recaps, because I'm giving you a lot of information here. So, so the reconstituted graph G prime, which consists of the vertex set and then the original edges and the fill-in edges F sigma, always has at least one perfect elimination order. When we run the elimination algorithm, we will always end up with such a graph. We will always inevitably end up with a graph that possesses a perfect elimination order, because we run the elimination order that we used again. And this is regardless of the elimination order. So no matter what elimination order you use, when you reconstitute the graph, that same elimination order will be a perfect elimination order in that reconstituted graph. Perhaps this is a very suggestive bullet point, isn't it? Perhaps we should only deal with such graphs. From the perspective, from a computational perspective, maybe that makes sense. So like, if we're inevitably going to reach such a graph that contains a perfect elimination order, maybe we should only deal with those. Now, before we can even answer that question, we need to basically be able to characterize such graphs. Okay. Now, is finding the order that minimizes the fill-in optimal? That was a question from last time. We shall see. And that I believe is going to be on your first homework problem set. So I'm not going to answer that in class. But that's a good question. I can't remember who asked that last time. We can characterize the complexity of a given elimination order. Yes, we can do that because it corresponds to the largest set of neighbors along the way of elimination. But it's problematic because if you use a greedy strategy, if you greedily do this, then that may not be good, because at some point you get to this point where, oh, suddenly you have this vast army of neighbors that you have to, and you have to eliminate that variable, and you're sort of stuck with the decisions that you've made up to that point. So greedy doesn't always work. So since such graphs are inevitable, let's define them and give them a name. Okay, so let's call them a perfect elimination graph. I think I already said this. So a perfect elimination graph is a graph that actually has a perfect elimination order. And we have already said this as well. Okay, so if we run a perfect elimination order on a perfect elimination graph, then the complexity is going to be equal to the largest clique in that graph. Okay, so let's just do a couple of sanity checks. Is this a perfect elimination graph? Yes. Does anyone recognize this graph? It's a hidden Markov model, which happens to be a tree. Right? So a hidden Markov model is a tree. For you sequential processing types, you realize that you've been working with trees all these years. What about this? Is this a perfect elimination graph? Yes, because we can eliminate this guy, this guy, this guy, this guy, and this guy. Those are leaves, right? And then we can eliminate this guy. There's no fill, and then this one, and just do it this way, right? That's a perfect elimination order. What about this one? So what if we eliminate this one first? Is that going to create fill-in? No? It would create fill-in there, right? Okay, so that's not going to work. What if we eliminate this one first? Whoops. If we eliminate this one first? Is that going to create fill-in? Yeah, right there. So that's not going to work. On the other hand, what if we eliminate, say, this one? That's fine. And then we eliminate this one. And then this one. And say this one, and this one, and this one, and this one, and this one. And then we're left with a 3 clique, and then we can eliminate any order we want. So that's a perfect elimination graph. Okay, question?
Sorry, so like 3 slides ago when you showed the hidden Markov model,
Yeah.
I'm used to seeing a hidden Markov model with directed edges.
Yep.
So you have the hidden states, and you're moving along states over time, and then each for a given hidden state emits a signal. So I'm used to seeing with arrows, and wondering why are there arrows?
The arrows don't make a difference. So we didn't talk a lot about the semantics of Bayesian networks yet, but I can give you a little bit of a tip on that. So basically, in a Bayesian network, which probably you're used to seeing a Bayesian network version of a hidden Markov model, it's the same as an undirected model if it's the case that there are that there's never the case that there's more than 2 arrows going into any given node. So if you look at a hidden Markov model, every vertex has at most 1 incoming arrow, right? And so when you moralize that, and it doesn't have any, it doesn't create any additional moral edges. And so it actually turns out that in the case of a hidden Markov model, whether you add the edges or whether you add the directions in a Bayesian network case or you don't in this Markov random field case, it's exactly the same family of probability distributions. So they're both a hidden Markov model. I should be, if I were to be very precise linguistically, I would say they both correspond to the family of distributions that can be represented by the hidden Markov model family. Because the hidden Markov model is a family of probability distributions that factorize in this particular way. And whether or not you describe the family, in this case, as a Markov random field or as a Bayesian network where you have arrows, doesn't matter. Same family.
You can also graphically represent a conditional random field, right?
Well, that's another topic. But yes, conditional random fields, at least the chain conditional random fields that you typically see in sequential processing, also correspond to a conditional distribution that is a conditional form of the same distribution that lives in the hidden Markov model family. So a conditional random field, as it's typically being used, is just a conditional form of hidden Markov model. So it's the same distribution. You're just doing probably A given B, but where the joint is still the same family. Yep.
Will we be discussing moralization at some point?
Do you want to talk about moralization? Yeah, we can talk about moralization. I haven't talked about Bayesian networks. So what we'll do is the following. So we will finish the discussion of triangulation, all this kind of stuff, and exact inference with Markov random fields. Then we'll talk about Bayesian network inference. And so what it turns out, I mean, I'll give you a brief preview, I guess, is that when you're doing inference in Bayesian networks, the stuff that Bayesian networks can do, namely the V-structures, don't offer you anything computationally beneficial over what you can do in the space of, at least for exact inference, that what you can do in the space of Markov random fields. So the first thing that you do is you moralize a Bayesian network. And what moralization does is it removes the expression of the V-structures in a Bayesian network. And then you're left with a Markov random field, which might or might not be a perfect elimination graph. And then you still have to do elimination, then turn it into a perfect elimination graph. But we'll talk about the semantics of Bayesian networks. I think that's important. But let's get back. Maybe you can ask that question again when we talk about Bayesian networks, and that will be more clear. How about this? Is this a perfect elimination graph? Who says yes? And who says no? So let's do it together. So can we eliminate that guy? Can we eliminate this guy? And what about this guy? What about this guy? What if we eliminate this next? That's bad. Can't do that. So let's not eliminate that guy. What if we eliminate this one? Yep. What about now, can we eliminate this one? Yep. What about this one? And now what are we left with? For clique. We can eliminate in any order we want. Doesn't matter. Right? It's a very disguised for clique. When you look at, you're going to see this that depending on how we draw a graph, it can make it look like here's the for clique, right? You know, maybe it doesn't look like a for clique, but this is exactly the same as C, D, F, and K, where it's a for cycle where you have cross edges. So it's the same graph, just the vertices are in different position. What about this? Is this a perfect elimination graph? So where might you start?
C.
Yeah, clearly we start with C. Are there any other vertices that when eliminated would not cause any elimination? Not cause any. Sorry, which one? G. And we might as well also do D. What next? B. And now what do we have? We have another for clique. So we're done. Right? Okay, so basically, when running the elimination algorithm, this is a very important theorem. When we're running the elimination algorithm, so we're eliminating vertices, then all max cliques in the resulting reconstituted graph are encountered as elimination cliques during elimination. So first of all, let's remind ourselves what an elimination clique is. So when we're eliminating variables, we're about to eliminate this variable, so that variable and its neighbors become completed, right? So that becomes a clique. And that is what we're calling an elimination clique. Does that necessarily mean it's a max clique? And remember, a max clique is our name for a maximal clique. It's a clique that when we add any node to it is no longer a clique. It's not connected. So there's some vertex that's not connected to some other vertex in that bundle of variables. So so then we run the elimination process, right? We get this reconstituted graph, which we know to be a graph that has a perfect elimination order, or perfect elimination graph. And there are some set of maximal cliques, the set of maximal cliques in the graph. So remember, there's the clique factorization property and the max clique factorization property. These are the maximal cliques, the cliques within which all non-maximal cliques can be placed inside of. And so what this is saying is that all maximal cliques are encountered as elimination cliques when you run the elimination process. So here's the proof. So each elimination step produces a clique, right? Like I just argued, but not necessarily a max clique. And so the set of maximal cliques, I'm going to try to sort of break these into logical steps in terms of color. So the set of max cliques in the resulting reconstituted perfect elimination graph is the subset of the set of cliques encountered during elimination. Right? So what we're saying is that the elimination cliques are a superset of the set of max cliques. And the reason for this is because of the neighbor property proven before. So remember, when we eliminate a vertex in the original graph and then in the reconstituted graph using the same elimination order, the neighbor set is the same. If there was a max clique in the reconstituted graph, so let's use orange for this or something. If there was a max clique in the reconstituted graph that was not one of the elimination cliques, okay, that clique would be encountered in a run of the elimination with the same order on the reconstituted graph. Right? Because you're going to eventually, the first vertex of that clique is going to be seen, right? And moreover, the first vertex in that clique that's seen is going to have that max clique as a neighbor. Or all of the nodes of that max clique as a neighbor. But because of the theorem 4.3.2, it has to have the same set of neighbors that it encountered in the original graph, which would contradict the fact. It would contradict this fact here. It would contradict the fact that a max clique in the reconstituted graph was not one of the elimination cliques. So therefore, it must be the case that all maximal cliques are encountered during the elimination process. Okay, so that's good. Now, how do we then identify? I think this is the next theorem. No, this is not the next theorem. But one of the things we'd want to do is, okay, so we've got this list of cliques from the elimination process. That doesn't actually give us the max cliques, right? It gives us a superset of the max cliques. So one of the things we want to be able to do is identify the set of max cliques. So here's the theorem that we want to prove next. So if we've got a graph, G, and an ordering sigma, and a reconstituted graph G prime, then it's actually fairly easy to get the set of max cliques in G prime from the elimination order. And here's basically how we do it. Here's the theorem. So should I talk it or should I do it on the slides? Let me just talk it first. So basically the idea is, so when we eliminate a vertex, right, that vertex and its neighbors are involved in a clique, right? Now that vertex and its neighbors might be a max clique or might be a subset of some max clique. But any max cliques that we encounter in the future of the point that we eliminate that vertex, this guy can't be a subset of that max clique because those max cliques don't contain V anymore because V has been eliminated. So basically, V and its neighbors at the time that V is eliminated either has to be a max clique or a subset of some other earlier encountered max clique, right? So what we do is the following. We sort of keep this list of max cliques. We sort of keep we start building this list of max clique. And if it's ever the case that a vertex and its neighbors are not a subset of the set of max cliques that we've previously encountered, then we say it must be a max clique. And so we add it to our set of max cliques. Okay? That's basically what this says. So should I say that again? Or you could just rewind it and hear it again. I'm going to push forward, but I'm going to say that it therefore is the case that the following must be true. If you eliminate a vertex, the first vertex that you eliminate and its neighbors, there is no previous set of max cliques, so it mustn't be a subset of any previous max cliques because there are no previous max cliques. So it basically means that the first vertex and its neighbors must be a maximal clique. That's this term here. The first node that you eliminate along with this neighbors forms a maximal clique. Okay. So one thing I want to point out is that a node can be a member of more than one max clique. Yes, that's true. So take, for example, this graph here. So there's two max cliques here. There's this max clique, and there's also this max clique. So that means that this guy and this guy are both members of two max cliques. Let me ask you another question. Is there a bound? I mean, obviously n is a bound, but is there strictly less than n a bound on the number of max cliques that a node might be a member of? Sorry?
It should be its degree of sense.
It's like its degree, that's right. N minus 1. Yeah, so like, that's exactly right. So we have a star, say. So that vertex in the center is a member of all max cliques. Every one of those edges, this is a tree, right? In a tree, what are the max cliques? The edges. And so in this particular graph, that vertex in the center is a member of all max cliques, which is in this case is n minus 1. Okay, is everybody okay with this theorem, basically? If it's not clear, then read through it again. So this is something that we've sort of said before. So we're starting with this graph, VE, in this factorization property, and we've got some member of P. But computationally, we inevitably are working with this family, this larger family, where we're adding the fill-in edges. So the kind of questions that you might have in your mind are things like, for example, can we identify the smallest such larger family? We've already seen that there are some graphs that don't have any fill-in, that there are, if we start with a perfect elimination order graph already, there's no fill-in. Other graphs necessarily are going to require some fill-in. So anytime we do any summation of variables, we're going to be increasing the family computationally. But the question is, we want to increase the family the least amount, right? Because remember, every time we grow the size of the largest clique, the complexity is going to increase by a factor of r. So it's growing exponentially fast as a function of the number of variables in a clique. So we want to make if we care about asymptotic complexity in some sense, we want to make the size of the largest clique as small as possible. And before we answer that question, we're going to answer the second question, which is, does there exist a property or a characterization of graphs other than having a perfect elimination order that characterizes this family of graphs? And we're going to see, and this is how we're going to wrap around this discussion back to trees. We're going to see that it turns out that those graphs that have a perfect elimination order are intrinsically related to trees. Let's take a break and ponder the possibilities of these kinds of definitions that might allow us to gain better intuition on what a perfect elimination graph is. So we'll come back in a minute. Okay, let's continue for the second portion of today's lecture. This notion of embeddability of graphs is a very general graph theoretic concept that people have used. We're going to use it from the perspective of embedding one graph into a perfect elimination graph. But in general, basically, we're saying that any graph can be embedded into another graph if it's the case that the other graph has a superset of the set of edges. So that basically means that the graph that can be embedded into the other graph is what's called, and these are the official terms for this. This is called it's called a spanning subgraph. So let's say that G is the graph into which we can embed a graph G. So that means that G is a spanning subgraph of G prime. Now, if you've heard the term spanning tree before, it's the same spanning. It's basically a subgraph that happens to be a spanning subgraph that happens to be a tree. That's called a spanning tree. It basically means that you have the same set of vertices but a subset of the set of edges where the edges constitute a tree. But in general, that terminology is used to convey the notion of a subgraph as well as just a tree. And so basically, whenever we embed a graph into a larger graph, the embedding process never shrinks the family. And so what this means is that the elimination process where we add these additional fill-in edges basically gives us a graph into which we can embed our original graph. Okay? In other words, any G can be embedded into G sigma, where G sigma is the reconstituted graph corresponding to the elimination order sigma. And so what we're essentially doing when we're running elimination, again, this is from the computational perspective, what we're doing is we're essentially embedding G into the class of perfect elimination graphs. Okay? And we want to do so in some sense, like we want to find the embedding that causes the least harm, right? Or causes we want to find the graph into which we can embed our graph that has the best computational properties. Now, this was getting back, I think, to Chandrasekhar's question about, for example, does this restrict us in any way? Now, when we do this embedding process, are there any members of the family that are excluded? No. We have, remember this picture, we have the set of all possible distributions, U. And let's say that we have this, which is the set, this is the family of distributions, say V and E, with some Markov properties. And let's say that this is yellow or something. And then we have a larger family, necessarily larger family, where this corresponds to the graph into which we're embedding the original graph. So that basically means that any member of this original family is still a member of this larger family. So we are totally fine to do this from the sort of representational power perspective. We aren't decreasing our ability to represent distributions. Does it change the resulting query values that we get? Like, let's say, okay, now I've got this embedded family, I've got this larger family, now I want to compute the probability of x2 given x3. Does it change that? No. All answers are the same. Everything is exact. Why? Because we're solving something in a more general category. This is really important. This also, by the way, getting back to the discussion of Bayesian networks, this also is very related to the moralization process. Moralization is exactly the same. Yep, question?
Is the determinant size related to the choice of using exact inference or approximate inference?
Well, so here's what approximate inference might do. So approximate inference might do is say, so you're starting with that yellow family. Approximate inference might say, here's a smaller family, and find me the closest distribution in that smaller family. That's essentially what approximation inference is. It's like approximation inference says, your original distribution is no longer valid in the family I'm working with, but on the other hand, the family I'm working with now is very, very computationally tractable. It's not exponential. But from amongst all of the distributions that have this nice computational property, find me the closest one. So we will talk about that. But now we're not talking about approximate inference.
So you always lose some space.
We would lose some fidelity. We'd lose some, that would cause distortion. And sometimes it can be pretty bad distortion. And what you're trying to do there is you sort of have, it's a different kind of constraint. Like, is the most important thing fidelity of the query? Do we want the right answer to the query at the least amount of compute? Or do we want to bound the compute and for all possible models with bounded compute, find the one that has the best fidelity? That's like structural learning and approximate inference. So in fact, here's an example of structural learning. So like I mentioned this. It's funny that this bullet point is here right when you're asking this question. So again, you're anticipating bullet points, which is great. So a possible structural learning strategy idea would be to start with some probability distribution in this family. And you find some spanning subgraphs. So now G prime is the actual subgraph, where E prime is a subset of the original edges, like E prime might be a tree, and solve inference in this subfamily. Now it turns out, by the way, I'll mention this, that for trees we can do this optimally. We can find the optimal tree, but for other classes of graphs we can't. But we will talk about this later in the course. Okay, so the class of graphs called triangulated graphs is really important. So triangulated graphs are sometimes referred to as chordal graphs, or rigid circuit graphs, or monotone transitive graphs, or perfect elimination graphs. And we're going to see that the perfect elimination graphs, the graphs that have a perfect elimination order, are the same. But we want to understand and be able to view them from multiple perspectives, because it seems like when we run elimination, when we do message passing on a non-tree graph, we're inevitably going to end up with one of these graphs. And so this essentially allows us to see a very different way of characterizing these graphs. And so the definition of a chord, so a chord, when you first hear about this, is a little bit confusing, but a chord is always with respect to a cycle. So you've got some cycle. You've got some cycle in the graph. So in this graph on the left, the cycle is this this thing here. So here's a cycle, which I'm highlighting in red now. Okay. There's a cycle, and a chord is with respect to some cycle. And so in this, on the middle case, the chord is the blue thing. Right. So a chord is basically two vertices with respect to a cycle that are non-adjacent, and that connect two non-adjacent nodes. But the adjacency of the nodes is with respect to the cycle. So the reason why, moving on this one, that this is a chord is because this node here and this node here are not adjacent on the cycle. This node here and this node here are adjacent on the cycle, so that you can't really have a chord there. But it might be a chord for some other cycle. Okay. What about here in this graph here? Is there a the one on the right here? Oops. Is there the cycle is highlighted in bold, or just in case it's this? Is there a chord in this cycle? No, there's no chord, because we would need to have something like that. Okay, a triangulated graph. The definition of a triangulated graph is the following: a graph is triangulated, or equivalently, it's chordal, if it's the case that all cycles have a chord. Sometimes you say that all cycles of length 4 or larger have a chord. But I'm in this class saying that all cycles have a chord. And the reason why you can say that, I think, is because here you have, in a triangulated graph, any cycles of length greater than 3 must have a chord, right? But any cycles of length 3 have no non-adjacent vertices, right? So any cycles of length 3, all vertices are adjacent in that cycle. So in some sense, it rules that condition out right away, just by the nature of the length of the cycle. So what are some examples of triangulated graphs? Well, these include things like a clique, right? Any set of variables that are fully connected is a triangulated graph. Why? Because all pairs are connected. So any cycle must have a connection between two non-adjacent vertices in the cycle. Right? Now remember, again, it's always with respect to a cycle. So in a clique, everything's connected to everything. So anything non-adjacent, I mean, everything is adjacent to everything in the clique, but once you designate a cycle, you can talk about non-adjacent vertices in the cycle, but which, in this case of a clique, must have a chord. So a tree is triangulated. Any tree is triangulated because there are no cycles. It's just a condition on cycles, but if there are no cycles, then the condition is satisfied. A chain is triangulated because it's a tree. So that means that a hidden Markov model is triangulated. Any set of disconnected vertices is triangulated. So if you have a bunch of independent random variables, the graph corresponding to that is a triangulated graph, since there are no edges. There's no cycles. Another important property is the hereditary property of triangulated graphs. It basically says the following: so if you start with a triangulated graph, that if you take any node-induced subgraph, so what is a node-induced subgraph? Basically, you choose a subset of the nodes, and then any of the edges that reside between the sets of nodes that you remain, that you still have. And the reason why it works is the following. Let's say that you start with a triangulated graph, and there's no chordless cycles. And so you take a vertex, and so that basically means any vertex you take, there are going to be no chordless cycles through that vertex. So if you don't consider that vertex, all you're doing is eliminating cycles. But once you don't, there's still not going to be any chordless cycles through any of the other vertices any of the other cycles that don't involve that vertex. So if you remove that vertex, there's still not going to be any chordless cycles. And then you can just repeatedly do that until you get to the subgraph. Okay, some questions for you. Which other following graphs are triangulated? Let's see if this works. So let's start with this one. How should we do this? Let's start with this one. Is this triangulated? Yes. Is this triangulated? Yes. Is this one triangulated? No. It's not? Where's are all cycles chorded? It is triangulated or is not? I saw a lot of people nodding their head. This is a deliberately tricky graph. This is the same graph as this one. Right? So if this is like 1, 2, 3, 4, and this is 1, 2, 3, 4, and this edge here is the same as this edge here. So all cycles have a chord. Got it? Just rearrange the vertices. So
the chord is just one chord.
it basically says that all cycles must have a chord. So you choose any. There might be multiple ones. There might be a single one. It basically says any cycle you choose must have a chord. So pick a cycle, any cycle. Pick a cycle, any cycle. Are there any? If you take two, does there exist two non-adjacent vertices of that cycle that are connected? If yes, then the chord is cycled. Right? That's the condition. Okay. What about this? Is this triangulated?
Yeah.
Yeah. What about these two? These two here. Yep. What about these two? Yep. Here's the hidden Markov model again. That one we know is triangulated. How about this one?
Yep.
What about this one? We saw this one before. Yes, this is triangulated. And what about this one? We saw this one before too. Yeah, I mean it's you know this now maybe because you're going to see. In fact, we've already said that graphs that have a perfect elimination order are triangulated. Here's some new ones. So is this triangulated? No, and the reason why is because there are chordless. This cycle is chordless. How about this graph? Is this triangulated? No, and why?
The 4 on the outside.
That's right. There's an outer cycle. This one doesn't have a chord. It would need to have a chord. What about this 4 cycle? Is this triangulated? No, that's an easy one. What about this one? There are a lot of triangles on this one. Does this have a chord? Or sorry, is this triangulated? Does it have a chord? It has a chord. If we take this cycle, is there a chord of that cycle? Yeah. So is it triangulated? No. Why is it not triangulated?
Take the outer edge of the side.
Which one?
Take the entire outer edge.
Yeah, the entire outer edge. That's a good one. We would need to have a chord, or even there's smaller ones. What if we take this one? Is there a chord on that cycle? No. Is there a chord on this cycle? Yeah. So it just basically means that there has to be, for a graph to not be triangulated, you have to find one cycle that doesn't have a chord. As soon as there's one cycle that doesn't have a chord, it's not triangulated. What about, I don't know if we should keep going with this, but what about this one? No. What about this one here? No. No. Not. Here's a hard one. What is this one triangulated? These are beautiful pictures. You don't realize how long it took me to do these. Is this triangulated?
No.
Yes, no, yes. Let's see if we can do this. If we take this,
4 corners.
this, and this, and this. Is that a cycle? Yes. Is there a chord? No. That's not triangulated. What about this one down here? Which kind of looks like a star of some sort. This one here. In fact, these two graphs are the same, aren't they? These are exactly the same graphs. They're just different rubber band stages. You know, it's basically, do we stretch the edge around here, or do we have the edge go this way? It's exactly the same graph. So that's what I'm saying. Like, when you look at graphs, depending on how you look at them, the properties might be readily apparent. Like, remember this one here, this one here. In the bottom case, it was obviously apparent, but if you look at the top case, you see this very, very prominent apparently chordless cycle, but then you forget about this edge. So human nature tends to get in the way of mathematical truth, or I should say human intuition.
Pattern recognition problem? Easy to recognize.
Is it a pattern recognition problem? I think it's probably just a trickery, a sort of a visual trickery problem. I think that it's just, there's a big science to how do you display a graph. Like, there are lots of different ways of displaying graphs which are entirely isomorphic. Sometimes the way you display it conveys the information that you want to say, that you want to see or you want to convey. Other times, the display of the graph does not convey the information that you want to see. And so when you go to lay out a graph, laying out a graph is very important. I personally have many times had it be the case that a student will come to me with a graph and I have no idea what it does until I relay it out in a way that to me makes sense.
Which means there is some semantics in the layout itself.
It's either a semantics in the layout, or it could be a deficiency of my ability to convey the information regardless of the layout in the graph. But I think most people are probably the same way. I think most people probably have preferred ways of laying out a graph. And this is true for graphical models as well. So when you're using graphical models, it's important to, like, let's say you want to use a graph in a paper to be published. You want to make sure that it's laid out in a way that very, very efficiently conveys the information that you want to convey. That's what we say graphical models are good for. The visual representation is sort of an efficient communicative mechanism to provide the reader with information quickly, right? So, and if it's a very convoluted graph, it doesn't do that. Okay, so let's move forward. The last one you can solve on your own. So let's do a couple of more definitions. So there's a notion of a simplicial vertex in a graph. So basically, a vertex is simplicial if it's the case that its set of neighbors are complete. Right? So, for example, if this is the graph, then this guy is not simplicial. This guy is simplicial. But if we add these edges, then this one becomes simplicial because its neighbors are complete. So basically, the simplicial vertices, you're eliminating vertices in a graph. If you eliminate a vertex, and if its neighbors are complete, then that guy happens to be simplicial. So what does that mean about trees? So leaf nodes are simplicial, right? In fact, leaf nodes of trees and simplicial vertices of arbitrary graphs, or in particular triangulated graphs, will be seen to be very comparable because they both lead to no fill-in when you go to eliminate them. So now this theorem says the following. You're starting with a graph G, okay, and elimination order sigma, okay, and then you eliminate that and you get this perfect elimination graph G prime, okay, which is G sigma. So we may reconstruct a perfect elimination order. Like once we've got the reconstituted graph G prime, okay, once we've got that reconstituted graph, we can then reconstruct a perfect elimination order with respect to G sigma, or the reconstituted graph. And how do we do that? How do we do that reconstruction? By repeatedly choosing any simplicial node and then eliminating it. Okay, so we know once we've got the reconstituted graph that there's a perfect elimination order. So we know that it must be the case that there exists a series of simplicial nodes, and that each case we eliminate the vertices. In the case that we keep eliminating simplicial, we know that there is some sequence of at the current graph simplicial vertices. But let's say we do this. Is it going to be exactly the same order as the original one, or is it not? Whatever it is, before we answer that question, let's just call that order sigma prime. Now what the theorem is saying is that, well, it might not be the same order. Sigma prime might not be the same order as sigma. However, both are perfect elimination orders for G prime, right? So, I mean, it should be clear that if it's the case that it's a series of simplicial vertices, that it will be a perfect elimination order, because just by the definition of a simplicial vertex, when you eliminate a simplicial vertex, we're not adding any fill-in. So both orders, or any of the orders that have that property, are essentially simplicial. But then let's just prove the first part of the theorem. So if there is more than one possible order, we reach a point. So at some point, like we start eliminating simplicial vertices, and at some point we reach a point where there's a choice, where there's two possible simplicial vertices, u and v. And maybe the original order eliminated u, and the new one you're thinking about eliminating v. So if we were to eliminate u, that does not render v non-simplicial. Why? Because both are simplicial, and when we eliminate either of them, it adds no edges. So no new edges are added. And if no new edges are added, then v, if anything, it either has the same set of neighbors or it has a reduced set of neighbors. If it was the case that u was one of v's neighbors, it would have a reduced set of neighbors. If it's the case that it's a completely different set of neighbors, it would have the same set of neighbors. But it certainly isn't rendering v non-simplicial. So that basically means that v remains simplicial. So what this means is that each time we eliminate a simplicial node, any other node that was simplicial in the original elimination order stays simplicial in the new elimination order when it comes time to eliminate it. So both elimination orders work, and they're both perfect elimination orders. Okay, any questions about this theorem? Yeah, question.
So I was confused about terminology. I got confused. G dash is the reconstituted graph.
Yes. That's your only question?
Yes.
Okay. Good. Okay, a couple of definitions related to separators. So separators are really important. It turns out that we can characterize triangulated graphs just by properties of separators. But before we do that, we need to define certain aspects of separators. So what do we mean by a separator? So first of all, what is an A-B separator? So we have two vertices, A and B. A set S is called an A-B separator if it's the case that all paths from A to B go through S. So the picture, I mean, the rough, like, let's say here's a graph, and here's A, and here's B. So that means that this set is a separator, is a separator. Okay. Is any subset of that yellow bit also a separator? Well, do we absolutely need to have this guy in the separator? What if we just took, whoops, what if we just took this as a separator? That would also be a separator, right? Okay. So there's the notion of minimality of a separator. So a minimal separator is a separator that is no longer a separator if you remove any node. So going back to this graph here, taking this yellow bit, and if you remove any node, then it's no longer a separator, right? Why is that? So if you remove this node, then there's this path, right? That opens up that path. If we remove this node, then it opens up this path, and so on and so forth. So that's clearly a minimal separator, but it's not minimal if that part was part of the separator. Okay, so we've got a separator and a minimal separator. The next we need is, these are both with respect to two vertices A and B. So we have an AB separator and a minimal AB separator. And the notion of just a separator without any association ascribed to that separator with respect to, say, A and B is a set of vertices if there exists some AB for which it is an AB separator. Question?
Do we allow A or B to be in S?
Do we allow A and B to be in S? No, because basically the idea is that S is something for which separates A from B. So we have to go from A through S into B. So we say that A and B are not in S. Okay, and then lastly, there's the notion of a generic minimal separator is a set such that there exists an A and B such that S is an AB minimal separator. Okay, so here's some more examples. So in the left example, both x3 and x4 and x2, x3, and 4 are x1, x5 separators, but only x3, x4 is a minimal separator because x2 is redundant. In the middle example, x3, x4 is no longer a separator because there's an edge now between x2 and x5. This edge exists now. However, in order to get a separator between x2 and 5, we would need to now add back in x2. So now x2, x3, x4 is a minimal separator. And on the right-hand side, this is an important example because it's showing that x2, x4, and x6 is a minimal x1, x3 separator, right? So let's zoom in on this one. So x2, x4, x6 is a minimal x1, x3 separator. But can there be one minimal separator which is a subset of another minimal separator? The answer to that question is yes, because x2, x6 is a minimal separator for x5, x7. Okay? And here's some more examples. But I think this is pretty clear to everybody. Raise your hand if this is not clear. Okay, question? Wait, did you raise your hand meaning that it was clear?
Yeah.
Okay, so raise your hand if this is clear.
Can we say empty set with the empty set the minimum separator
Yes. So if you have two connected components, if your graph which consists of two or more connected components, then the empty set is a minimal separator of any vertex in the corresponding two connected components. That's right. So a minimal separator could be the empty set for a graph that's not, that consists of multiple connected components. Okay. This is an important theorem. What it states is the following, is that let's suppose that S is a minimal AB separator in a graph G. Okay? And so now, let me just add a page for this. So, because I think this is, hold on a second. So in general, when you're a separator, say a minimal separator, so this set in the middle here is, let's call this guy, this set here, let's call this S. And let's call this vertex A and this vertex B. Okay. So there could be some other vertex C. So whenever you have a separator, you've got sort of, there's the component on the left, which involves S and A, and the component on the right, which involves S and B. But there could be some other component, S and C as well, right? So in some sense, a set, and some people even use this terminology. You can think of a separator as something that shatters the graph into a number of pieces. If you're starting with a graph where everything is connected to everything either directly or indirectly, and then you have a separator, it shatters the graph into at least two pieces. And if it's an AB separator, there's a piece which involves A, there's a piece which involves B, and there might be other pieces which involve something else, or there might only be two pieces. Okay, but these are called the connected components associated with the separator. There could be two or more of them. And what the theorem in here is talking about is the following. It's saying that S is a minimal AB separator, so it's a minimal separator now. And we're letting GA and GB be the connected components of G once S is removed. So it necessarily is the case that S, if you're starting with a connected graph, and S is a separator, it shatters the graph into different pieces, each of which is connected. So in this case, these things that I've highlighted in green are the connected components. And there could be lots of other stuff as well involved in all this stuff as well. Like there could be other pieces of the graph here. But because it's a separator, this piece can't connect to B. Because if that was the case, either directly or indirectly, if that was the case, then S wouldn't be a separator. So, therefore, it makes sense to name these subpieces of the graph, these connected components, GA and GB, to be the connected components of G once S is removed that contains A and B. So here we're sort of abusing notation. We're saying that these two connected components, GA and GB, are a subset of the set of pieces of the graph, of the pieces that S has shattered the graph into, which is notated G with V without any of S in it. The key point is that A is a vertex of GA and B is a vertex of GA. And the critical thing that the theorem is stating then is that each S is adjacent to both some node in GA and some node in GB. So why is this? Let's just get some intuition by looking at a picture. So let's say that you are this separator. And here's A. And here's B. And so the separator is in green, and A and B are on the left. What the theorem is saying is that while the green stuff is the separator, it can't be a minimal separator because it's not connected to some node in GA and some node in GB. Like in particular, notice that this node here, let's call this guy orange. Well, first of all, what is GA? So here's here's GA, and here's GB. And that orange node is not connected to any node in GA. It's connected to every node in GB. There's only one node in GB. But it's not connected to any node in GA. And so therefore, this stuff here can't be a minimal separator. That's what the theorem is stating. So that if you're a minimal separator, and you separate it into these components GA and GB, where GA and GB are the components that contain both A and B, respectively, that it must be the case that every node in S is connected to some node in GA, and every node in S is connected to some node in GB. That's what the theorem states. And to prove that, it's a very simple proof. It's basically saying, suppose to the contrary, that in a minimal separator there is some S that's not adjacent to any node in, say, GA. Okay? Then if we remove that S, then the removal is still an A-B separator, because you can get you can sort of bypass that vertex because you're not connected to anything in GA. You can sort of get to S, and there's no way of getting, say, from that vertex. This would be this example here. There's no way of getting from this orange vertex to anything in GA without going through something else that's in S. Right? And so therefore, this guy that I highlighted in yellow can't be minimal, which basically contradicts the minimality of the separator. Okay? So therefore, that's true. So all minimal separators, all minimal A-B separators are such that in the component GA and GB, you're connected to somebody in GA and you're connected to somebody in GB. Okay, so that's an important lemma. The next, does everybody understand this, at least the statement of the theorem? Okay. The next theorem is super important. Okay, so basically it says that in a graph is triangulated if and only if it's the case that all minimal separators are complete. So in other words, all minimal separators are little cliques. Doesn't mean that they're max cliques, it just means that they're cliques. Okay, so how do we prove this? So suppose that it's an if and only if condition, so we have to do both sides. So suppose it's the case that all minimal separators are complete, right? Now we have to prove that the graph is triangulated. To do that, let's take some cycle. So the cycle we're going to take is U, and that's going to be connected to V, and that's going to be connected to W, which is then connected to X1, X2, ... to XK, and XK is connected to U again. So there's some cycle, okay? Now, basically, we're assuming that all minimal separators are complete. So then when you could think about, we're thinking about minimal UW separators, right? So V must be part of a UW separator, right? Because if we don't have V in the UW separator, then there's a path between U and W. So another possible path between UW, by the way, that was unintentional, calling this UW. I know this is the name of our school. Maybe I should have called this, I don't know, like MIT. So if there's an MT separator, no, never mind. So see, this is all related to UW stuff. So here's another path from U to W, right? So basically, there must be some pair V. So V is part of minimal separator, and there must be some other X somewhere along this line, which is part of a minimal separator, right? Let's just say it's some X. But basically, since it's the case that all minimal separators are complete, that basically means that this edge constitutes, this edge right here, this yellow edge, constitutes a chord in that cycle. But the cycle is completely arbitrary. So therefore, all cycles have a chord. Therefore, the graph is triangulated. So starting from all minimal separators are complete, we've gotten triangulated graphs. Now the converse is the opposite, or the converse is the converse. The converse basically says, let's first assume that the graph is triangulated, okay? And then let's say that S is a minimal AB separator, okay? So here's the picture down there you can sort of think about. So S is a minimal AB separator. So here's GA on the left and GB on the right, and A is somewhere in GA, and B is somewhere in GB. So here's A, here's B, and S is a minimal AB separator in this triangulated graph. And what we're trying to prove is that S is complete. Okay. So we have from that previous lemma that every element in S must be connected to somebody in GA, and every element in S must be connected to some element in GB. Why? Because it's a minimal separator. And moreover, we have that GA is connected and GB is connected. And so therefore, there must be some between any S and T in S, there must be some shortest path which consists of only nodes in GA. And similarly, there must be some shortest path which consists of only nodes in GB. Right? So let me ask you this. So why can't there be this edge here? If there was that edge, then that wouldn't be the shortest path, right? So that means that none of the A1 through AM can have any other edge other than the ones that are adjacent along that path. Similarly, this can't exist as well, for the same reason. It's the shortest possible path. Similarly, this can't exist as well. Why? That would violate the fact that it's a separator, right? So but we've got this cycle, right? So the only possibility to chord that cycle would be to add this edge. But S and T are arbitrary inside of the separator, so that must mean that S is complete. So we use the minimality to make sure that everything was connected, that everything in S was connected to something on the left and something on the right. Therefore, all minimal separators in a triangulated graph are complete. So therefore, we've proven the theorem. And I think I've already said all this stuff, so I don't need to go through it. But anyway, if the theorem isn't clear, then just read through it and listen to it again. But basically, what I said here in this slide is also what's down here. Okay. Okay. So the wonders of triangulated graphs. So like I said, there's a bit of theoretical stuff. If you were very happy, lecture 1, and you thought that this was a very simple class, like I've said to you before, there's opportunity for intricacy and detail, and we're beginning to see some of that. If you have any questions, please post it to the forums. Why? Because then everybody gets to see the question. There will be a homework set out soon, by the way, so you will have to understand this stuff. Okay, see you soon. Have a good weekend.